I'm going to be talking today about data visualization, and I'm going to be doing it in my favorite data visualization software, which is R, but we'll get to that in a bit. I want to talk a little bit about the procedure of data science. This is from this figure right here is from a textbook on data science in R. And we might think of this as the data science pipeline. So we have some data out here, and then we need to import that data. We need to tidy it up, and then we iterate through this cycle of transforming the data. That could be adding new variables, computing summaries or transformations of other variables, visualizing the data, which is what I'm going to be talking about primarily today, modeling the data, which is a lot of the statistical models, the machine learning models, trying to understand what's going on with the data. And then we iterate back, and maybe we learn something from our machine learning model or our statistical model, and then we create a new feature to capture something that was missing before, or we create a new interesting visualization based on the outputs of our model. And we iterate through this a few times, and then hopefully, eventually communicate our findings to people who are not stuck inside here in the cycle of transformations and visualizations and modeling. So this might be communicating insights to business decision makers. This might be communicating insights to doctors or clinicians. This might be writing a scientific paper to summarize your findings. So that I'm going to use this as a guidepost for what the procedure looks like. Now, what I do, I guess you all know this, but I do biomechanics research, and so I deal with a lot of data that is very high dimensional and very complicated. So I'm going to load in an example of some of the stuff that I do and show you. So I deal with data like this. So you could imagine somebody running, and we have estimates of the motion of every joint in the body and the force in every muscle in the body. As you might imagine, this gets very, very complicated very quickly. But I'm not going to talk so much about my particular research, but I might use some examples from it as an avenue to discuss what this cycle of data science looks like, and with a specific focus on visualization. And I'm going to be talking specifically about doing data visualization in R, but the ideas are transportable to MATLAB or Python or whatever your favorite data science software package is. So why use R? I think R is pretty great. I'm a big fan of it. It's very powerful on really two big fronts. One of them being statistics. So if you want to use cutting edge, state-of-the-art statistical models, those are overwhelmingly published as R packages. So top statisticians or biostatistics researchers will develop some new interesting statistical type of model. And in addition to their publication, they'll also write and distribute an R package. So R is fantastic for statistics. And the other thing that it's really great for is this thing called the Tidyverse, which is a family of packages for data science. And maybe the authoritative resource on that is this textbook, R for Data Science, which is where that original figure came from. And this fellow right here, Hadley Wickham, he created the Tidyverse, which is this family of various different packages that are amazing tools for all of the steps in the data science pipeline. So R is amazing for importing data and tidying data, although we're not going to talk too much about that today. And then all of these steps as well. Now, disadvantages to R, probably the big one is that it is not as strong for ML, meaning machine learning. There has been some uptake of, there was a family of packages called Carrot, which tried to do what scikit-learn does for Python, in that it unifies lots of different types of statistical models under the same API. I believe this has now been turned into something called Tidy models. And there is still a rich community of people who do ML and R, but you generally don't have quite as easy access to the cutting edge machine learning stuff. So if you come up with some new deep learning model, you're probably going to distribute it in TensorFlow or PyTorch, which of course is much easier to interface with through Python. So for my purposes, I generally do both. If I'm doing machine learning stuff, I do Python. And if I'm doing statistics or data cleaning or data visualization, I tend to lean towards R. Now, the reason I'm such a fan of this Tidyverse family of packages in R, and the reason why it's really a killer app for me, is that it was developed, like many of my favorite software packages, was developed with one coherent vision or philosophy that really came out of course, a team works on all these things, but one person came up with a specific vision of how data visualization should be done, or how data cleaning should be done. So pop quiz, does anybody recognize any of these four gentlemen right here? I have these pictures up here because each of these fellows had and is responsible for one of these kind of visionary software packages that has a clean, unified philosophy. So this fellow over here invented something most of you have heard of called Python. This is Guido van Rossum, Dutch programmer. This guy over here created the Tidyverse. This is Hadley Wickham. He is the guy who wrote that textbook I mentioned, and we'll be talking a lot about his philosophy of data science and philosophies of data visualization. This is Francois Cholet. My French is not so good. He works at Google and developed Keras, which is a very elegant and expressive framework for deep learning. And probably the least known of these four people, this is Simon Wood, a statistician at somewhere in the UK. And he developed an R package I quite love called MGCV, which is for semi-parametric regression. And I think we might see a little bit of that today. But these fellows are all up on here because I think there's clear advantages to having one unifying vision of the right way to do something, or a way to do something. So let's talk a little bit about this pipeline, especially going from here to here. So all the data I'm going to be showing you has already been tidied, and there is actually a whole philosophy of what tidy data is. There's even an academic paper on it written, no surprise, by this guy. So the tidy data philosophy is essentially as follows. Every row is an observation and every column is a variable. And what you're looking at right now is something that is very not tidy. This is raw data output from a wearable sensor that I'm using for some research. And you can see it's a colossal mess. We have different variables stored in the same column, and we have observations spread across over here and over here and over here. And it's a colossal mess. And the tools that you use, maybe pandas in Python or the Tidyverse packages in R, a lot of them are geared towards taking your ugly data and importing it, cleaning it up, and tidying it so that this is the same data. If you're wondering why these are blurred out, it's because these are GPS coordinates, and I probably shouldn't be sharing those with the world. But now we have every row is an observation. Every row is a timestamp from this wearable device. And I've got the latitude, the longitude, the distance covered, the power, altitude, speed. Every column is a different variable. One thing to be aware of, this is a format of data called this is specific to time series data. It's called wide format data. And then I have the same data over here in what we call long format. And that's just, do you store different variables for each timestamp in different columns, or do you say same timestamp here, 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 and then here's the three variables I care about? But the point is, we're going to start from having our data nice and tidy like this and not ugly like that. And if you want to read more about the philosophy of tidy data, there's a paper called Tidy Data that's a pretty good read on it. So that's a philosophy of how you should format your data. How about a philosophy of how to visualize your data? So there's a very influential book, which I have not actually read, but it was published in 1990 something, 1999, I think, called The Grammar of Graphics, which outlines a philosophy of how you should think about data visualizations. And it looks like this. You start at the bottom and build your way up. So you've got your data. Maybe we should write tidy data. You've got your nice, tidy, clean data set. And then you can set out an aesthetic mapping. So if we were to think about the most old school way of visualizing data, which is drawing it by hand, an aesthetic is like a mapping, right? Maybe you make a mapping of weeks into the semester and your stress level. I've set up an aesthetic mapping. I've mapped some X variable to the X-axis, some Y variable to the Y-axis. And then once I've set up that aesthetic mapping, I can put geometries on top of that. So maybe I make a scatter plot, right? That's one kind of geometry. A different kind of geometry might be a line plot, right? So same data, but a different geometry on top of it. You can also do what are called facets, and this is something that will be maybe easier to see than to talk about, but maybe that yellow line is my stress level as a function of time this semester, and here's yours. And then here's somebody else's. I should use a different color for that. And here's somebody else's. And here's somebody else's. What a facet would do is say, okay, I want to take this plot, and then I'm going to facet it by each person. So instead of getting one plot, you would get a 2x2 grid of plots, each of which would have the same X and Y axes, and each of which would be based on the same underlying data, but filtered so that maybe this person's data is here, and this other person's data is down. Oops, the other person's data is down here, and so on. You can also do statistics, and this means these interact with like your geometries. So maybe the most familiar example of this is a histogram. So a histogram takes the raw data, it maps one variable to the X-axis, and then it uses a statistical summary to count up how many data points are in each bin that you're using for your histogram. Finally, on top, you have coordinates, which set maybe the X-axis scale or limits, or maybe you do a coordinate transformation like a log scale. And then on top of this, you can layer on a theme, which is like colors and the background and the fonts. And the nice thing is that about this philosophy is that you can switch up different layers without affecting the other ones. So you can easily move from a scatter plot to a line plot to some kind of two-dimensional density plot to something with a certain theme or a different coordinate transformations without having to completely redo everything from scratch. And if you're familiar with doing data visualizations in Python or especially MATLAB, it's not nearly this easy to smoothly transition from one kind of data to another. The other thing I want to talk about with regards to data visualization is one important question that you always want to ask yourself when you're doing one, which is, am I making an exploratory data plot, or am I making an explanatory data plot? So am I trying to explore the data I have? Is this for me and my team to understand? Or am I trying to explain and communicate to other people what's going on? So getting back to this figure here, exploratory data visualization is down here. I read a paper recently that was summarizing most important statistical discoveries of the last 50 years. And along with things like machine learning and causal inferences and the bootstrap, exploratory data analysis, or EDA, was highlighted as one of the most important discoveries, developments in statistics in the last half century, which is interesting. We might connect explanatory plots with communication. So I have a few examples I can give of being on either end of this spectrum, because there's a few different rules that apply. I have a story actually about what can happen if you confuse these two. A few years ago, I was working on a project to try to find patterns in a certain set of high dimensional data. And so I did a bunch of research and reading about cool ways to do clustering and visualization of high dimensional data. I found something cool called TSNE, which maybe Gokchen can tell you about. I think that's, we have a resident high dimensional embedding expert that's more knowledgeable on this than me. But I threw all the data into this model and got these really cool results, and came to our lab meeting with this plot, which I thought it looked pretty cool. I thought it was really interesting. But if you're not an expert in this, you just look at it and you say, well, what is this? This is like a Andy Warhol abstract art. This is not what I was looking for. So this was an instance where I was trying to present an exploratory data plot in a situation where I should have been trying to use a explanatory data visualization. So when you're just exploring, it's totally fine to be sloppy with not getting the formatting of your axes correctly, or just just playing around with things and seeing what works and seeing what doesn't. And that's generally what we'll be doing once we jump into the live coding in R. This is a diagnostic plot I made when this was back in April, and I was doing a Kaggle competition to predict COVID cases in different countries. This is another this is a faceted plot, faceted by country. But you'll notice, like, there's no actual labels on the y-axis here, and there's various improvements we could be making. But that's a time investment that we wouldn't need to put in if this is just a plot for us to understand how is our predictive model behaving, and is it doing what we think it's doing or not. These are exploratory data plots. Whereas if you're trying to explain, you have to go the extra mile to really get some nice coloring and label your axes and so on. So this is for a paper I was working on this winter, and really going the extra mile to get everything formatted nicely. And this is really important, but it can slow you down if you're just making plots that nobody else is going to look at and you're just trying to explore. So exploratory versus explanatory, I think, is always a good question to ask yourself. Which of these two am I trying to do? So with all of that, I want to jump into doing some live coding. So I'm hoping this will be a little bit more of a freewheeling segment here, and we can actually just do some exploring. I gave myself a little bit of boilerplate code here to import the Tidyverse package and do a little bit to read in the data, and then do a little bit of a hack to get the plots to show up a little bit bigger to make it a little easier for you. So I'll just run these and it'll spit out some input output stuff. I have two data sets here, both of which I'll maybe send out in an email after this. So, well, two data sets, and I've read in four different data frames, four different data sets from these Kaggle folders. So I think we'll start with this liver data frame, and you're going to be seeing me use this this pipe operator here, which is, I guess, I'm not really a big history of programming person, but I guess these are popular in functional programming languages like Haskell, and I think Perl maybe has something like this. What it does is it just takes what's on the left and it puts it as the first input to the function on the right. So if we just take a look at this liver data set, I think this is from patients in India who either did or did not have liver disease. So you've got a bunch of patients and a bunch of different, I think these are like liver enzymes. And then our outcome of interest is whether or not this person has liver disease. So we can start visualizing this. So I'm going to take the liver data frame and I'm going to pipe it into the ggplot function, which is the core workhorse for data visualization in the Tidyverse. So we're going to set up our aesthetic mapping, just like our grammar of graphics suggested. So we'll do aesthetic. And let's just look at the distribution of this total bilirubin. I think it's some kind of liver enzyme. So if I do this, it will create a plot, but there's nothing on it. The reason there's nothing on it is because I haven't added any geometries yet. I have data, I have an aesthetic mapping, and now I'm going to add. Let's do geom histogram. Let's just look at a histogram. So I get a distribution like this. Okay, that's kind of interesting. Like many data related things you bump into, income is like this, sale prices are like this, biomarkers are like this. This is not very not normally distributed, right? And this is very highly skew right. So we can layer on a coordinate transformation. So let's do scale x log 10. So now this is a little bit easier to see. Like I was saying, it's easy to switch this out to something else. Maybe we can do, instead of a histogram, we can do a kernel density plot. So this is like a non-parametric version. Okay, cool. Maybe I'll fill that in so you can see it. Now, one of the things we might be interested in is, does this bilirubin level differ between people who do and do not have liver disease? So I can just go back to my aesthetic mapping and say, let's make a different distribution plot with a fill by whether somebody has liver disease. So let's say fill equals, and I think, what was it? Has liver disease was the variable. Let's try that. Uh-oh. There we go. Okay, so the problem there was that has liver disease was coded as 0 and 1, which is being interpreted as a continuous variable, in which case, but we want it as a factor. And this is, let's make this kind of see-through. Okay, so it looks like people who do have liver disease seem to have this more highly, there are like more people on the high end of this bilirubin biomarker, right? This is a biomarker. What about maybe is this a differential effect based on sex? So here's something we can do. Let's do a facet. Let's do facets wrap by, and I think it was labeled as gender. Okay, maybe I'll stack these on top of each other. So it looks like there's not too much of a difference between women and men on this, but this is a nice illustration of how quickly we were able to build up and iterate around that cycle of visualize data, model it, transform it. We've gone around that cycle like 3 times in the last 5 minutes and gotten some insights on this. Something that we can also do, maybe let's go through this again and look at something else. Maybe we can do, let's do on the x-axis has liver disease. And I'll show you one of my favorite ways to visualize things. Let's look at alkaline phosphatase. I think that's an enzyme, maybe. So I'm going to set up an aesthetic mapping, and I'm going to get an error because I forgot to close my parentheses. And again, nothing going on here because we don't have any geometries on top yet. But maybe I can just do a scatter plot, geom point. Now, this is going to start out being pretty unexciting, but we can do things like adjusting the position of the scatter geometry. So I'm going to do position equals position jitter. I'm going to add width equals 0. Maybe 2. That's too wide. There we go. So here is a way that I like to visualize data, because we can see every individual data point. As long as the data set size isn't too colossally huge, we can visualize it. And again, it looks like whatever this biomarker is, having a high level makes you more likely to have liver disease. Maybe we can add a splash of color. Maybe we can color by whether they have liver disease. That looks nice. And again, we might wonder, what about maybe is this different between men and women? So maybe what if we did, instead of color, we did color by gender? Well, now that's not so good because they're right on top of each other. But now I can do, instead of position jitter, let's do position jitter and dodge. Dodging is like taking things and offsetting them by some factor. And if I do that, now I've got females who have liver disease over here, males who have liver disease over here, females who don't, males who don't. I can even layer on top multiple geometries. This also looks like it's maybe non-normally distributed. So let me do, and I apologize, I'm being kind of sloppy with my code formatting here. For whatever reason, Kaggle does not have good like indenting intelligence to figure out like how to indent things when you put it down. But maybe let's do scale. Now we're going to scale Y. Log 10. Do that. So, okay, interesting. By the way, one other thing you can do, instead of scaling using the coordinate transformation to scale, you could also just do log like this, and you'd get the same result. An astute observer would note that, as is the case with Python and other programming languages, log without anything does a natural log transform, whereas what I had earlier was log 10. Although an even more astute observer would know that it doesn't actually matter from a visualization perspective, at least, whether you do a natural log or a log 10 transform, because it's just a multiplicative scale. So it will look the same. You just got to be careful to remember which way you visualized it. Okay, I think I've showed off the cool thing. Oh wait, no, I wanted to show one more thing. I wanted to show layering on top another geometry. So let's do geom. I like this thing called a geom violin plot. So it's like a density plot, but it's like flipped around and vertical. And let's do alpha equals 0.2, so we can see through things. So okay, that's informative. Maybe there's something goofy with why it's being dodged more than the others, but this is just an example of putting on top multiple geometries under the same plot. So again, the idea here is we're iterating through this, visualize the data, try a transformation, I guess this is like a very simple form of modeling, splitting into different strata to see if the relationships hold. Let's look at the Sydney data set. This is housing prices in Sydney, Australia in, I don't know, the early 2000s. So same thing. Well, let's take a look at it first. If you're wondering what this piper operator, what the functionality here, that command is the same thing as this. So it's just piping in that as the first argument. So it's a bunch of houses, sale price, and then lot size, and a bunch of statistics about the neighborhood, everything from crime rate to pollution levels. An interesting thing about this data set is that it is, I forget it is geographic data. So we have longitude and latitude. So we can do Sydney data frame. Let's do x equals, and I'm probably going to get this, I would get this wrong if I didn't have a cheat sheet over here. I always forget whether you should put latitude on the x-axis or the y-axis. And it is on the x-axis for longitude. Okay. So I'm going to set up an aesthetic mapping where x is the longitude, y is the latitude. This is just, I'm making a map right now. So set this up and there's nothing on it. Geom point. So let's just see where our data points are. So this is a pretty big data frame. So there's a lot of stuff. One easy trick to get around that is just set the transparency really low. Maybe we can even set it to like 0.1. Now, one thing about geographic data and like latitude, longitude data is that getting the axes to scale the same way is important, meaning you want one unit of moving to the right on the x-axis to be the same as one unit moving up on the y-axis. So this is another thing a coordinate transformation is useful for. So I'm going to layer on top this chord equal transformation. And this is now like starting to map onto what you would see on an actual map. So the outcome we care about, of course, is the sale price of the house. And one thing we can, well, let's in a cell down here, let's just do a quick histogram of that. So it is sale price camel case. Maybe we do a density plot, look at it, and to not really surprising, this is highly, highly non-normally distributed, right? Because there's a few houses that go for $10 million, and that ruins things for the rest of us in a number of ways. So we could do, maybe we can just do log 10 for reasons that will become clear. That's actually quite a nice, almost perfectly normal distribution. So if we were doing a regression model, we might be interested in trying to predict the logarithm of sale price as opposed to sale price itself. It might work out a little bit better. So one thing that you can do on a 2D plot like this is color the data points by the outcome you care about. So like sale price. And I'm going to do log 10 of sale price. So now we can see there's, okay, there's some like more expensive houses here and less expensive houses down there. I'm actually going to import another package for color mapping that I like a little bit better. It's called Viridis. And this is going to show off a, oops, not down there. This is going to show off another use of coordinate. I think it's technically a coordinate transformation. What we're going to do is we're going to scale. This is like scaling. You know, we did scale y log 10. We're going to do scale color Viridis. And let's do option equals. Viridis just has a couple nice color maps is all. So you get this nice, this is the four Viridis color maps are Viridis, Magma, Inferno, and Plasma. So they're fun names. So this is now starting to look much more understandable in that we've got these really expensive houses in here with this kind of space in the middle, and then much cheaper housing out here. Sydney is a city on a harbor. And so if you're wondering why there's nothing in here, this is because that's where Sydney Harbor is. The Sydney Opera House, it turns out, is right where my mouse cursor is right now. And that's where the really expensive houses are. Go figure. because if you want to live right next to a world landmark, it's extremely expensive. So these are some tricks you can use for visualizing and modeling and understanding geographic data. And the one other thing I wanted to show you is with this car data set. So this car data set is actually from Kaggle. And it is a list of a bunch of cars that were for sale on Craigslist. The version I have in this Indiana MLRC data set is a pared down version of, I think, maybe 20,000 of them, but the full data set is like over 1 million. So I think I used the same data set for the regularization talk that I gave like a year and change ago. So maybe, again, we're interested in price. Maybe we do car df, ggplot, and maybe just do an old-fashioned histogram of the price. And just like we saw with housing prices, turns out car prices are not normally distributed either. So maybe we scale x log 10. Okay, so here's a distribution of cars. Here's, cheap cars like mine that are worth, barely $1,000. Here's your typical $10,000 car on Craigslist, and then got more expensive stuff out here. Maybe where you'd be interested in the price of a car as a function of the year it was made. That would be interesting to explore. So maybe we could do car df. On the x-axis, I want the year. On the y-axis, I want the price. Maybe I can make a scatter plot. And I think this will take a few moments because it's a pretty big data set. Okay, and then same thing, we'll probably do alpha equals 0.2 so we can actually see what's going on. And then let's scale y log 10. So I mentioned when I was introducing the idea of statistics that the statistics as statistical layers on top of your plot, that a histogram is a really simple example of a binning and counting statistic. But you can do more interesting statistics, and I think you can even do custom statistics to transform this. So here is the distribution of, or here's year and car price on the y-axis. One thing that might be useful to do, well, okay, why is there an empty gap right here? Anybody know? This is cars made in the United States primarily. Anything happen in like 1940 to 1945? So yeah, World War II. No cars were made during World War II because all the factories were making tanks. So something you can discover from visualizing your data. One, I was on the topic of statistics, statistical layers. One you can do is, it's actually a geom, but the geom plugs into a statistical thing. We can do geom smooth. And I'm going to override the default here because it's very, very slow. And I'm going to use Simon Wood's MGCV package to fit something called a generalized additive model, which should give me a smooth, which should try and estimate the price of a car, really the log price of a car. And I think I should probably, will this work? I might have to log transform the Y, but I guess we'll see. Should give me the price of a car as a function of the year it was made with a smooth function that's estimated from the data. Oh yeah, okay, very nice. Maybe I can make that a little bit bigger. Size equals 2. There's another data set that I've worked with for a class that is apartment prices in Warsaw, Poland. And you can see a similar gap of no houses being built during World War II. And then you can also see gaps when there was civil unrest during the rule of the communist regime. Quite interesting. So this is a nice visualization. It looks like the cheapest cars on Craigslist were made in about like 1998 or so, 1995. And then the value of a car increases as it gets closer and closer to this year. Back up here, this is probably like, this is like muscle cars and, Model Ts and collectibles. So that was, I think that's roughly everything I wanted to show off. We could do some stuff with faceting plots by, I think there was one. I can do one more. I got one more cool thing on my cheat sheet over here that maybe I'll just show off. So maybe we could look at the distribution of price of cars in different states. So I've set up x-axis is price. I'm going to fill the geom density based on the state the car is listed in. And then I'm going to facet by state as well. So this might take a little bit because it's going to have to estimate 51 or 52 different. Oh no, that was pretty quick. So here's the distribution of car prices in all 50 states in the country. Perhaps maybe not super insightful as is. Maybe we could do n call equals 5. Maybe make it a little bit bigger. Some of this might be just this scaling of the plots that I had set up way back up here. Okay, no, that was not helpful. Okay. Well, in any case, faceting, you can also facet by different things. So that was everything that I wanted to show off. Does anybody have questions or thoughts? Data visualization.